published 4 breakthrough papers in physics. Now, for a little context, I'm currently pursuing my master's. This year, I'm going to publish 1 scientific paper, and to be honest, it's pretty weak. Einstein published 4 scientific papers, all 4 of them complete breakthroughs. The first one was a mathematical proof for atomic theory. He proved the existence of atoms. It was hotly debated until then. We're able to study atomic theory. We're able to study chemistry more accurately because of Einstein. Additionally, his energy mass equivalence was put in a paper that year. That's E equals mc squared, maybe one of the most famous physics equations. Again, special relativity was published that year, which is a phenomenal breakthrough understanding that unified a lot of issues in theories of light and electrodynamics. Finally, he published a paper explaining the photoelectric effect, and this is the one we're going to focus on today. The photoelectric effect is something that happens when we shine a light on a metal plate. If we get the right kind of light on that metal plate will eject an electron. And I say an electron, but what I really mean is it'll eject lots of electrons. One piece of light will eject 1 electron. I say piece of light, and that'll come back up later. But scientists were able to set up this experiment. They would have a battery attached to an ammeter, which would measure electric current, which is the flow of electrons, and they would shine a light on this metal plate and see electrons flying off of it. But that wasn't just the weird part. I mean, sure, you could say light is energy. You throw some energy at an electron, it's bound to get moving. But what was weird was it would only happen when they hit it with certain types of light. So let's take zinc for an example. Let's say this plate right here is zinc. If they shine red light on that, nothing would happen. Blue light, nothing would happen. Infrared light, radio waves, nothing would happen. It wouldn't be until they hit it with higher frequency ultraviolet radiation that anything would start to happen. And then all of a sudden, the higher the frequency of light, the more activity they got. And so there was this sudden point where it was just suddenly on. That didn't make sense to people. That didn't make sense to scientists. So what Einstein was able to do was show that there's this thing called a photon. And he built off of the work of Max Planck. And Planck had this idea about photons, that light actually travels in these tiny little packets of energy. We could almost call it a particle, like we could call an electron or a proton, but a photon has no mass whatsoever. And so a photon is going to be carrying a certain amount of energy based on its frequency. And so Einstein was able to establish that equation. So we have the energy of a photon is equal to this letter h times its frequency. This letter h is known as Planck's constant. Planck's constant. And it is equal, cross my T, it's equal to 6.626 E negative 34. It's an incredibly small number. And once again, this is a multiplier. This is like pi or the Boltzmann constant we saw in Coulomb's law. So why is this relevant? Well, it's relevant because it kind of explains why we saw this sudden change. When we hit a certain frequency here, then all of a sudden, our photons are carrying enough energy to get these electrons excited. And so we've got these little packets of energy. A single photon is going to hit one of these electrons. And if it gives that electron enough energy, that electron can then move away from the atom. It's like, think of an asteroid having to hit the Earth hard enough to knock it out of its orbit with the sun. We have to hit it pretty hard. And so we're able to use this idea to do something called photoelectron spectroscopy. And that's going to be the subject of the next video. But before we get there, my experience with a lot of first-year chemistry students is they don't really know anything about light. So let's talk about light. Let's talk about what light is. Light is an electromagnetic wave. And when I say wave, what I mean is light travels through space, vibrating back and forth, a lot like an ocean wave would. And so the light would be traveling this way, but vibrating this way. And that vibration, we can measure how many times it's vibrating per second, and we call that a frequency. frequency. Now, light moves at a very specific velocity. This is a universal constant. It's actually in special relativity, Einstein's theory of special relativity defined the speed of light to be the maximum possible speed in the universe at 3e8 meters per second. This is 300 million meters per second. It's represented by a c. You might recognize that in the E equals mc squared. That's 3e8 squared. Interesting. So that frequency of light, it's going to be traveling this way, and it's going to be vibrating back and forth. And so we could also say that the distance between this part of the wave and where the wave starts to repeat, so right here, we could give that a name. We could call that a wavelength. So let's call that a wavelength. And we represent a wavelength with the Greek letter lambda. We represent a frequency with an F, and sometimes you might see a little cursive V like that. I tend to use F. That's what we use in physics. I think it's silly that we use the V because it's F for frequency. That's all over the place. The only time we ever use this is sometimes in chemistry to talk about the photoelectric effect. It's silly, so we're not going to use it. So what is the relationship between a wavelength, frequency, and that velocity? Well, it's a very simple equation. It's going to be C equals lambda F. So the frequency times the wavelength will always result in the speed of light. And so when we talk about light, when we talk about different types of light, things like radio waves, microwaves, things like ultraviolet radiation, you may have heard of some of these before. But let's just start with visible light. Visible light is going to be on this part of the spectrum. It's going to be photons traveling with a very specific energy level, a very specific frequency. And anything in here, as we increase in frequency, increasing in energy, we start to move from red light to violet light. Now, if we get higher in frequency, we get to something called ultraviolet light. Ultraviolet being more energetic than violet. So we get UV radiation. You might have heard of this before. This is the type of light that shined on people in tanning beds to tan them. This light does come from the sun as well. Our ozone layer in the atmosphere is able to pick up and absorb some of this ultraviolet light so that it doesn't hurt us very much. But people can sit outside in the sun, and this ultraviolet light will cause them to tan. And if you do that too much, it can cause damage to your skin cells, irreversible damage to your skin cells, called leukemia. If we go even higher in energy, we start to get into X-rays. X-rays have so much energy that they don't even get stopped by the skin. They actually go right through it. And so X-rays will go through skin and bounce off of bones. And so we're able to use them to take pictures of our insides, which can help doctors diagnose different illnesses. And you may have also heard of gamma rays. Gamma rays are the scary type of radiation. Gamma rays possess so much energy that they will pierce through anything, including bone. And so gamma rays are able to get into cells, and they will ionize atoms, which can cause mutations, which can cause cancer and other radiation sickness. Now, thankfully, gamma radiation can be stopped by dense material, so a few feet of concrete or a few feet of water. So if you ever have a piece of material giving off gamma radiation, the easiest thing to do to get rid of it is just throw it into a swimming pool, and then it's not a danger to anybody. If we go less energetic, we get to infrared light. Infrared light is going to have a little less energy than red, and it's a very useful type of light because anything giving off heat is going to give off some amount of infrared radiation. And so we can use an infrared camera to see heat signatures of things. And this is commonly used in night vision technology. Going a little bit lower, we get microwaves. Now, you may have heard of this. Microwaves. In a microwave oven, a microwave is used to get water molecules a little more excited. When we get these water molecules excited, they start to vibrate. And when they vibrate, they heat up. And that causes food to get heated up. And so microwaves are able to heat things up by vibrating water molecules. And that's why a lot of things, when you put them in the microwave, end up being soggy, because it's water that's being vibrated. You're going to get some steam. We go a little less energy. The lowest type of energy, lowest electromagnetic waves that we have available are radio waves. Radio waves are everywhere. This is how our cell phones communicate. This is how our Wi-Fi gets transmitted. This is how Bluetooth works. This is how the radio gets into your car. The world is full of radio waves. Satellites are constantly communicating with the Earth using radio waves, and they all travel by that same speed of light.